We are Group 7 and our project is simulating riser equilibrium using computational fluid dynamics software. My name is Brian McCamley.
I'm Ross Teichman.
I'm Parker Jones.
And I'm Garrett Ruiz.
And our advisors are Dr. Tiagi and Dr. Akbari. Special thanks to Mohammed Bousaleh and Paul Sonneman for their contributions to our project.
One of the biggest issues with offshore drilling is the possibility of a gas kick entering the drilling marine riser. If a kick enters the riser and passes the BOP, you lose the ability to circulate that kick with the choke line. As a result, the kick must either be circulated out or allowed to migrate on its own. Either option results in gas expansion. So as the gas column is circulated and migrates towards the surface, the height of the column of mud above it decreases. The decrease in the mud above the gas results in a decrease in hydrostatic pressure on the gas. This decrease in hydrostatic pressure allows the gas to expand. This relationship is described simplistically using Boyle's law. Today's well control training uses Boyle's law to model gas expansion. If a kick's initial volume is known, Boyle's law is used to calculate what volume the kick will be at the surface. This procedure was what we used in our 4060 well control lab. For example, say we take a 3.5 barrel gas kick. It enters our riser at 10,000 feet below sea level just before we can shut in our BOP. The riser has a capacity factor of 0.35 barrels per feet, and it is filled with 12 pounds per gallon water-based mud. We can use the initial kick volume, the pressure at the bottom of the riser, which is just the hydrostatic pressure due to the 10,000 feet of drilling mud above it, and the surface pressure, which is just atmospheric, with Boyle's law to calculate the expected volume of the kick when it reaches the surface. In this example, we estimated that the 3.5 barrel kick will expand to 1,486 barrels, which results in a 4,245 foot column of gas in this riser. Say we did the same Boyle's law calculation for 23.6 feet below the top of the riser. This is the same process as before, except that this time the pressure at 23.6 feet below the top includes the hydrostatic pressure of that column of mud along with the atmospheric pressure. This tells us that the gas would expand to 742.8 barrels, which results in a 2,146 foot column of gas. This single calculation proves that the original calculated 4,245 feet is not possible in this riser. With the gas being much lighter than the 12 pound per gallon drilling mud below it in the column, the only way for the column to expand would be upward. You can see that there is only 23.6 feet left in the riser for the gas to expand upwards, which is much smaller than the 2,099 additional feet that the column would need to expand to meet the results of the first Boyle's law calculation.
If we compare the traditional model taught in well control school with the iterative calculation we performed, we see the error introduced when taking Boyle's law into account in our collapse load calculations. Assuming the seawater gradient is equal to 0.433 psi per foot and that the gas is weightless, we see that the traditional calculation of the gas volume at the endpoint of the riser gives a collapse load of 1,838 psi from the seawater pushing in on the riser. The calculation of the gas volume at 23.6 feet gives a collapse load of 929 psi from the seawater. With only a difference of about 20 feet, we see that an error of 50% is introduced into the predicted collapse load requirement. An important concept that's not included in Boyle's law is riser gas equilibrium, which is the point where the subsequent gas volume expansion suddenly becomes capable of thrusting all fluids above it out of the riser. This expulsion of mud may happen even if the gas does not migrate or get pumped upward an additional inch. Since this is not included in Boyle's law, there's no way that Boyle's law will be able to model the expansion of gas accurately.
Using ANSYS Fluent, we can simulate riser gas migration based on some key mesh and fluid flow parameters. Our annular mesh consists of a riser length of 1,000 feet. Our inner riser diameter is 19.72 inches, and our outer tubing diameter is 4.75 inches. This results in a fluid flow cross-sectional area of 287.7 inches squared. When considering frictional pressure loss of our model, the roughness coefficient of stainless steel will be used. This is approximately 0.015. Gas columns of varying heights will be introduced to the system, which will be circulating water at a rate of 0.4659 feet per second. Our outlet pressure will be set to atmospheric pressure, which is approximately 14.7 psia, and our inlet pressure will be constantly changing as gas migrates up the riser. This is an example of a pressure profile that we have generated through ANSYS of water circulation through our annular mesh. As you can see in the upper left-hand corner in the red box, our simulation will be run using transient flow and a density-based solver. The transient flow setting is used for flow calculations that will be based on time steps, and a density-based solver is best suited for flow situations involving compressible fluids, in other words, a gas. Through our research, we have found these to be the ideal solver settings for the two-phase flow we are modeling.
The main results that we will be looking at from our simulation to verify or disprove Paul Soneman's model is the riser equilibrium pressure and the riser equilibrium volume. The riser equilibrium pressure is equal to the square root of the pressure on the gas when it enters the base of the riser times the vertical height of gas when it enters the riser times the fluid gradient in the riser. The riser equilibrium volume is equal to the square root of the depth of the top of the gas when it enters the riser, which is equivalent to the depth of the riser, times the volume of the gas when it enters the riser, times the annular capacity factor of the riser per foot. We can find these values by looking at the results from our ANSYS simulation and finding the point where the riser gas expansion begins to increase exponentially. This point will be signified by a sharp drop in hydrostatic pressure at the bottom of the riser as the gas begins to take up more and more of the volume at the top of the riser at an exponential rate. Additionally, we will record the final volume of the gas once it reaches the top of the riser in order to compare it to the volume predicted to occur by Boyle's law. The velocity of the gas at the outlet will also be noted, because it may be that the gas is reaching supersonic speeds by the time it exits the riser, which would provide an explanation as to why the simplified models, such as Boyle's law, do not work. When comparing our data to the existing knowledge, the questions that we'll be asking ourselves after the end of our simulations are, can ANSYS Fluent simulate a dynamic model, and how does this dynamic model compare to Boyle's law? Are Paul Soneman's equations, as discussed earlier, verified or disproved by our model? And finally, what insights that we can apply to the industry can we gain from our project?
The first determination of our simulations will be whether ANSYS Fluent can accurately model the riser equilibrium phenomenon. Rapid expansion of the gas column should be seen to verify that the physics are well represented. We will also analyze the conventional Boyle's law calculations used in the industry to determine gas expansion. This standardized procedure is a conservative approach that ultimately lacks accuracy. Dynamic analysis of the riser equilibrium through ANSYS Fluent should allow us to more accurately determine the gas column present when compared to the conventional model. If we are able to provide a more precise determination of this column, we will be able to find a reduced collapse pressure for our system. This better understanding of the gas expansion process in the riser could hopefully lead to better applications of managed pressure drilling in the future. MPD can be utilized to provide a back pressure which can reduce the rate of gas expansion and can prevent severe unloading events. Our remaining work begins with completing our working model in ANSYS Fluent. This will involve implementing a discrete gas phase that is injected into our riser mesh. We will use back calculations to predetermine a riser equilibrium point, and we'll be able to analyze the fluid behavior once this region is reached. Rapid gas expansion should be expected at this point. We will also be simultaneously constructing an Excel spreadsheet. This spreadsheet will present us with gas and mud column outputs as a function of circulation depths. We will use it to compare outputs for the Boyle's Law method with outputs from the dynamic method represented with our ANSYS Fluent simulations. The spreadsheet will allow us to calculate and analyze error between the two methods.